For those of you who don't know me, my name is Stephanie Waterman, and I'm a physical oceanographer who, like Paul, works at the CCRC here at UNSW. An important part of this introduction is that I am not an ocean modeler. I tend to think of myself as an observationalist, which means that I go out and make observations of the ocean system and try to understand them. And on days when the system seems just way too complicated to ever understand, I dabble in probably what you would call theoretical oceanography, which is thinking about processes in a very idealized context. And so as a consequence, I was a little surprised when Melissa asked me if I wanted to tell you about ocean modeling. And I thought, well, why is that? And then I thought, it's maybe because they know that I am in absolute awe about what ocean modelers can do. And when I was thinking about what I should talk about today, I was reminded of an experience I had as a first-year graduate student, so maybe a similar stage to some of you in the room, where I had the opportunity to go to NCAR, which is the National Center for Atmospheric Research in Boulder, Colorado. And this is one of the centers in the US where they run these huge, all bells and whistles climate models and big supercomputers in the basement. And I remember in particular a conversation I had in the office of Peter Gent, who is the same Gent of the Gent and McWilliams parameterization, for those of you who think that deserves some celebrity. And he showed me some fantastic animations on his then very tiny computer screen of his ocean model in full Technicolor glory. And I remember him saying to me that it was pretty amazing that basically with just two ingredients, the solar input, the solar forcing, and our knowledge of atmospheric and oceanic dynamics, that we could produce simulations that got so many of the features of a large-scale circulation correct. And it's true, it is really amazing. And I think it's easy, especially when you're down in the trenches fighting day to day, to be consumed by all the challenges and all the things that we're not getting right. And there's certainly lots of those, and we'll talk about a few of them towards the end. But I think it's also important to remember that this is really, Paul talked a lot about remarkable human achievements, and I think that this is really a wonderful illustration of how much we do understand about the ocean circulation. And so it's important to remember that on days when things aren't going so well. All right, I decided to subtitle, I always subtitle my talks, to call this an ocean introduction for everybody. And the motivation for that was actually a conversation I had on Monday night over pizza with a young woman who studied climate extremes. And we were talking about how in these kind of events, people from different disciplines, the ocean people, the land people, the atmosphere people, all get together under this umbrella of climate science, and we're kind of made to talk to each other and talk at each other. And she was saying, you know, at these events, I always feel it's the oceanographers who do the poorest job at making it accessible and understandable and talking about ideas that are really, you know, accessible to an educated scientist. And I thought, well, okay, I'm going to try to rectify that a little bit. So for the most part today, I'm going to talk to the non-oceanographers in the room. But towards the end, I will try to entice some of the experts in the room with the challenges for the future. So if you could hold on to the end, that would be great. Okay, so by this point, it's day 4, and you've heard a lot about modeling. You've heard about climate modeling, land modeling, atmospheric modeling. Even if you had no idea about what ocean modeling is, I bet by now you could probably make a pretty good educated guess about what an ocean model is and the kind of things we put into it and the kind of things we expect to get out of it. Nevertheless, it's my turn now, so you get my take again. I think, from this view a little bit removed from the trenches, that an ocean model is a representation in the form of maybe mathematical equations or computer code that really describes physical processes that encapsulate our understanding of how the ocean works. And when we're talking about the ocean in particular, the types of physical processes we're talking about are any process that exchanges energy, mass, and momentum between the ocean and these external sources. So things like radiation at the surface, evaporation and precipitation at the surface, river runoff, wind energy that creates waves and imparts momentum into the ocean at the surface. We're also talking about all the physics and dynamics that describe ocean movement. So when I'm at a dinner party and I say I'm a physical oceanographer and then people want to talk to me about whales and dolphins, I say, no, physical oceanography is describing where does the water go and why. And that's ocean dynamics. And so that's another big element of your ocean model. And then an increasingly sort of problematic one is all the processes that get the energy out of the system. So all the processes that mix things away and that dissipate the energy. And this is a whole zoo of processes that occur on scales from the molecular to ocean basin scale. And we'll talk a bit more about those as time goes on. All right, so just as Steve Sherwitz told you, there are lots of different types of atmospheric models. There are, of course, lots of different types of ocean models, too. This is where I like to hang out in parameter space, which is sort of what we call conceptual or process models. And these are models that are very limited in the number of processes that they're considering and very limited in sort of the detail of the description of, that they're trying to describe. But they have some advantages. First of all, this limitation makes them potentially easier to understand. So if you want to just understand a process in isolation, these might be a good way to go. And also you have a bit more freedom because they're simple. You can, say, integrate them for much longer. Or maybe you can run hundreds of them to explore your parameter space a little bit more completely. Now, at the other end of the spectrum, of course, are all your bells and whistles, GCMs. It wasn't until I made this slide that I realized that GCM stands for both Global Climate Model and General Circulation Model. I never quite realized that. So these are the kind of models that we've been more talking about this week, and it's also the ones that I'm going to focus on today. But there, of course, is a broad spectrum of models for a broad spectrum of tools, or uses, I guess. Okay, so just as there are many ocean models, there are many ways to use ocean models. The one that gets the most press, I think, is to consider future climate changes. Everyone's familiar with that. But there are also lots of other uses that maybe get a little less press. There's a whole realm called operational oceanography that in academia we don't necessarily interact with maybe quite as much. But this is the business of making operational forecasts, nowcasts and short-term forecasts for governments and industries and rich yachtsmen who want to sail their yachts across the Atlantic faster. The third one is sort of maybe what a lot of you are involved in, and that's using ocean models as an experimental tool to further understanding of certain processes or certain phenomena. And I think as time goes on, if you look at an edition of Journal of Physical Oceanography these days, you know, the use of ocean models as experimental tools has really, you know, skyrocketed compared to if you look at an edition 10 years ago. And I imagine that trend will continue. This is a reason I like to use models. I have very sparse observations in time and space, and they're a great tool to help sort of interpret those operations from a mechanism perspective. And there are more. Okay. All right. So since you've already heard a lot about atmospheric models, and since many of you are maybe more familiar with atmospheric models, I thought I would start by introducing ocean models by telling you how they're the same and how they're different to atmospheric models. And so there's a few fundamental differences between the ocean and the atmosphere. So perhaps you didn't know, but that air is a compressible gas, and seawater is a nearly incompressible and relatively dense liquid. Okay? Now that has some pretty important implications. It means that if you take a parcel of air and you double the pressure, you're going to half its volume and double its density. You do that same thing to a parcel of seawater, not much is going to change. And that means that this requires sort of a fundamentally different equation of state. And Paul talked a little bit about the nasty equation of state that we deal with in ocean models. In the atmosphere, usually you can get away with assuming sort of an ideal gas law for your equation of state. And the equation of state describes the dependence of density on other variables like temperature and pressure. In the ocean, the equation of state is kind of a very complicated, poorly understood, nonlinear equation that's a function of temperature, salinity, and pressure. And as Paul mentioned, we spend a lot of time in ocean modeling just actually solving this equation in our set of primitive equations. But there are some like we get some breaks in other areas. In most cases, we can assume that the ocean is incompressible, and that makes it simpler. That means the water coming into a grid box is equal to the amount of water going out, and that leads to some simplifications. It's also a really nice way to filter out all the sound waves in your system sort of for free. But you shouldn't do that if you're interested in finding submarines. Okay. The second kind of big difference about the oceans compared to the atmosphere is that the oceans are, of course, salty. In reality, seawater contains a whole host of dissolved chemicals that we sort of collectively refer to as salinity. And salinity has an important impact on the density of seawater. And so we must sort of keep track of our salinity and how it changes and how it impacts density as we step our model along. In sort of an analogous way that the atmospheric models must keep track of humidity. All right, so vertical structure. The vertical structure of the oceans and the atmospheres have some important similarities and some important differences. So both have a relatively well-mixed layer, called a mixed layer, near the surface, where most of the heating and the cooling occurs. But the atmosphere, compared to the ocean, is actually pretty relatively well-mixed, even outside this mixed layer, while the ocean is much more stratified below its very thin mixed layer. And Paul talked a bit about some of the implications of this. This means that horizontal motions in the atmosphere are much more likely to dominate over vertical motions, and that can lead to some simplifications in our modeling efforts. And as I'm going to show, we can actually benefit from the fact, because the oceans are really stratified and because they're mostly forced from the surface, we can kind of exploit that fact by choosing some smart vertical coordinate systems that the atmosphere scientists don't get to use to make our job easier. Talk about those more later. Okay, a big difference that actually makes the ocean problem a little harder is the horizontal structure. So the atmosphere sort of blankets this Earth in this nice continuous layer, and it's pierced by some mountain ranges, but they're really quite small compared to the depth of the atmosphere. The ocean, in contrast, is bounded on 5 out of 6 sides by very complex topography. So we have this series of these irregularly shaped basins. They're fringed on the edges by these relatively narrow continental shelves with these really steep continental slopes. And we have this complicated bottom symmetry that actually, for the ocean circulation, plays probably an order 1 role in the deep currents. And so we can't really neglect the impact of that. We also have lateral boundary conditions in the ocean, so we have to keep track of things that are coming into the ocean from the edges, so river runoff and continental runoff. The need to really resolve both horizontal and vertical processes along the ocean margins, we'll see, plays a really critical role in choosing our grid that we tend to solve ocean models on. Are there any questions? Please do interrupt if you have any questions. Welcome back. Okay, finally, number 5, the final one is, Steve, I got angry in the back. Steve told you that atmospheric models are more expensive than ocean models for a given grid size. And that's very true. The time step in an atmospheric model has to be much faster. But what he failed to tell you was that the energy containing scales, what we call the geostrophic scales, in the atmosphere are much larger than they are in the ocean owing to the stratification. And what this means is that we need to model the ocean at a much finer horizontal spatial resolution in the atmosphere if we want to resolve the same types of motions. Also, because the ocean interior is pretty much adiabatic, and Paul talked a little bit about this, what this means is that the flow tends to follow along density surfaces compared to the atmosphere, which is relatively well mixed. Means that the equilibrium timescales of the ocean are much slower than that of the atmosphere. So if you want to spin up an ocean model from rest, it actually takes you thousands of years to get the deep ocean into equilibrium, which is much longer than an atmospheric model, which is much faster to equilibrate. Okay, so it's never a competition, but it kind of is. And so, so I would say, to be fair, ocean modelers have it both easy in some respects and hard in other respects compared to their atmospheric counterparts. So we definitely benefit from the fact that the ocean is nearly incompressible, and water in equals water out. And we also benefit from the fact that the ocean is strongly stratified and mostly forced at the surface, and so we can exploit some of the simplifications there. But we have our own problems to deal with. The domain geometry is really complex, and when we talk about grids, you'll see, the great lengths that people go to try to help in that respect. We need some lateral conditions and lateral boundary conditions, and actually they're quite poorly constrained. The eddies tend to be smaller, the spin-up time is longer, and this is a big one for me. There are a lot fewer observations for validation compared to our weather predicting counterparts. Okay. Any questions about that? Fine. Okay, you've seen these equations before many times. These, Steve described these as the fundamentals of an atmospheric model, and they are the same fundamentals of your ocean model, with just a few modifications. what to say. So the horizontal momentum is very similar to the atmosphere. We tend to, most ocean models in the climate model sense, assume hydrostatic balance. That means that we are neglecting vertical accelerations. That's going to have some important implications. We'll talk about that later. We conserve mass, and if we assume incompressible, that's the same thing as conserving volume in the ocean. Like the atmosphere, we have to conserve heat. We also have to conserve salt in the atmosphere. And then we've got this nasty nonlinear equation of state to deal with. Many people have told you that these are the equations that allow you to be the master of the universe. Is that what you said? You got 7 coupled equations and 7 unknowns to solve for. There's, of course, some other ingredients that you have to throw into your pot to make an ocean model. You need to give it some boundary conditions, and so you need to tell it what is the Bayesian geometry, what do the coastlines look like, what does the bottom topography look like, and then what does the atmosphere sitting on top look like. Either you've got to resolve that atmosphere dynamically or at least impose its effects on the upper layer of the ocean. You need to give your model some initial conditions, and that really is initial temperature and salinity fields and initial velocity field. These could maybe come from climatology, so like a mean state, in which case the ocean's probably at rest and you need to let it spin up, or from a previous already spun up model then. And then finally you need to give it some forcing fields, and in the ocean context these include all the forcing of temperature at the surface, so things like short wave radiation, long wave radiation, latent heat, and sensible heat. All the sort of salinity forcing at the surface, so your evaporation and your precipitation rates. You need to give it its lateral boundary conditions, which impact temperature and salinity, so the land surface runoff at the margins. And then the dynamic forcing, the winds, which again are prescribed at the surface, and the body forces given by tides. Yeah?
Might catch what you said about the mean state. So these are mean velocity fields, so you're talking about spinning up.
Yeah. Yeah, so that sort of came out of my mouth, and then I thought, yeah. So often, if you went to the World Ocean Atlas on the internet, which is a global database of observations, and took the mean climatology, it would give you a mean temperature field and a mean salinity field. And it might actually give you a mean, what we would call geostrophic velocity field, which is the velocity field in balance with those fields. And so you could maybe initialize your model with that, and then you don't need to spin it up in quite the same way. Often we do initialize our models from rest. You'd have to ask a real ocean modeler about why they do that. I don't know. Why don't we prescribe initial velocity?
Because the velocity spins up really quick, like relative to the thermodynamics stuff, right? So
okay.
The velocities kick in right away, and they're always going to be adjusting to that. It's changing temperatures and salinity.
But it's the deep circulation that takes a long time to adjust.
Not the velocity field.
It's the thermodynamic field.
Temperature and salinity, yeah. And so it's always, so there's really no
benefit.
And plus your model might just barf and crash.
Okay.
Am I wrong on that? Well,
all right. Okay. So that's all well and nice, and we can all write down the primitive equations, and they all look so beautiful in their analytical form. But on the ground, when you actually want to run your ocean model, there are a lot of practicalities that you need to worry about. And so let's talk about a few of them. First of all, we have to discretize those equations, obviously, and so we need to pick both a horizontal and a vertical grid and the resolution on which we want to solve those equations. And so let's talk a little bit about those issues. First of all, starting with the horizontal grid, you sort of have two broad choices for your horizontal grid. You have your regular grid, which I'll talk about here, and you have your irregular horizontal grid. And so your regular grid is exactly what it sounds like. It's pretty regular. It consists of regularly spaced lines. Now, it's important to remember that on spherical Earth, you can't actually have a uniform grid spacing and straight lines. So in practice, these grids tend to be a little curvilinear, and their internal spacing tends to vary a little bit. Now, regular lat-long grids also have a problem at the poles where the grid lines tend to converge. But here, oceanographers win. There's this clever solution. I don't know who to attribute this to. Do you know, Paul?
That's like, yeah, no idea. Like, I always call this Eulerian transformation, but I don't really know.
So they came up with this nice idea to get rid of the problem of this convergence at the North Pole. We can sit sort of a circular grid over the Arctic basin. Now we have two convergence points, but they very conveniently lie in the middle of Canada and Russia. So that's a very nice ocean solution for your convergence problem. So regular grids have some advantages. They're very computationally efficient. They have relatively straightforward analysis algorithms, and they really have benefited from decades of research experience. Now, most of your atmospheric models will run on regular grids. But for the ocean context, there are some disadvantages, and the biggest one is that for a given latitude, you sort of have a fixed resolution. And so if you wanted to increase, say, resolution near your margins or near your coastlines, you're kind of stuck with increasing that resolution everywhere around that latitude band. And so now you have very high resolution out in the middle of the ocean where you maybe don't want it. And so they're very inefficient in that respect. All right, and so really motivated by that disadvantage, smart people spent a lot of time thinking about better solutions. And this broad class is what people call irregular grids. And really, they're all designed to give you more freedom to put spatial resolution where you want it. Now, this came up yesterday in Marshall's talk. A common scheme is composed where you kind of make a mesh or a grid of a series of triangles. And this is what people call finite element modeling. And by varying the triangle size, you have a lot of freedom. You can construct this very non-uniform horizontal grid. You can put lots of resolution on your coastlines or on your mid-Atlantic ridge, and have coarser resolutions in the middle of your basin where the time and length scales are larger. So this seems like a great solution. So they're efficient owing to the fact that resolution can be tailored as a function of space. And they have this nice property that you can accurately represent coastlines and bottom bathymetry. There's this, what am I trying to say? There's this very common problem with staircase bathymetry in a regular grid that you can get rid of with your irregular grid. But there are a lot of issues with finite element modeling in sort of global scale ocean models. Marshall said yesterday when he said that they're a total failure or something, and I wouldn't go that far, but there are a number of issues, and these are some of them. First of all, actually, these finite element models have a lot of issues with flows dominated by geostrophy and advection, which are the two big characteristics of your large-scale ocean flow that is still being worked out. The other kind of interesting, this is a very interesting kind of theoretical problem, I think. These unstructured grids have spatially variable resolution-dependent physics. So it means in some regions, the physics that you're resolving is different from over here, where your mesh is a different resolution. And so really you should be starting to think about viscosity and diffusivity coefficients that vary as a function of space or as resolution. And I think this is a very unexplored and not well understood realm of research. In addition, there's this issue in ocean models with what they call numerical diffusion or spurious diapixel mixing that's associated really with a numerical advection scheme. And in these grids that have this variable resolution, you actually have this variable degree of that kind of problem, which is hard to understand the impacts of that. The list goes on, there's issues related to matching of the low resolution areas to the high resolution areas. So what do you do if in your low resolution area you have a parameterization turned on, and as you merge into the high resolution area, what do you do to that parameterization? That's a bit of an open question. The tools to analyze these irregular grids are still very immature relative to their regular grid counterparts. And they still are very computationally expensive. So low order, the rule of thumb is that low order finite element models are about an order of magnitude more expensive than finite difference models for the same degree of freedom. So you really have to be gaining a lot in the gains you're getting for resolution in order to make this worth it, right? So these unstructured grids are quite common in sort of coastal and estuarine modeling, where the coastlines with the symmetry are really important. But they're still very uncommon in sort of global scale ocean modeling. However, CLIVARS is an international group of ocean modeling experts. They're a working group on ocean model development. They make the prediction that a coupled climate model using an unstructured mesh ocean will emerge within a decade. So we can look forward to that. Any questions? Okay. All right, this is even more out there, but I wanted to put it as a slide because I thought it was really cool. So you can go further with this unstructured mesh idea and start thinking about meshes that actually dynamically adapt to the flow with time. And so this is this Imperial College ocean model that Marshall talked about yesterday, and it has a mesh that will, as at each time step or at each mesh refinement time step, it looks at the curvature of the flow and it puts resolution where it thinks it needs it in that flow. And they have, I couldn't find on the internet, they have this wonderful animation of just water sloshing in a cup with like sort of, you know, lobs of water coming up in the air. But they don't show you the fluid, they just show you where they're going to put the mesh. So you see this beautiful animation of this coarse mesh in a quiet cup, and then someone shakes the cup. And you see the mesh sort of all like coming out in space. It's fantastic. Very cool, but it's very much in its infancy for ocean modeling applications. Although I like this quote: there will inevitably come a point at which the additional overhead of uniform mesh refinement everywhere, even where you don't need it, is greater than that associated with finite elements in mesh adaptivity. So maybe in the future. Okay, so that's the horizontal grid. We have to also choose a vertical coordinate system. And actually, in ocean modeling, this is quite a loaded choice for a number of reasons. First of all, the oceans are mostly forced at the surface. And as a consequence, most of the action occurs in the upper ocean. The oceans are strongly stratified, as we said before. That means that horizontal motions dominate over vertical motions. The oceans are pretty much adiabatic in the interior, and that means that flow is mostly along density surfaces as opposed to across density surfaces. And then we've got this complex bottom bathymetry to deal with. And as a consequence, you know, there's a number of different choices for your vertical coordinate system in your ocean model have evolved. And so I'm going to talk about the three kind of traditional ones. The first is just an absolute depth or a Z coordinate system. And this is probably the one that you would draw first. It's just based on a series of depth levels. It's common to actually, if you want to put more resolution in the upper ocean, you can do that very simply in the system by just decreasing the spacing between your Z levels in the upper ocean relative to the deep ocean. This has lots of advantages. It's really simple to set up. It's very computationally efficient. There aren't these issues with pressure gradient errors that some of the other systems suffer from. But again, the big disadvantage is that it's a bit restrictive in terms of putting resolution where you want it. And in particular, if you want to have increased vertical resolution on your continental slopes, you're kind of stuck with putting that increased resolution all across the basin. There's also this issue that I mentioned with what people call spurious diapycnal mixing or numerical mixing. And this is the phenomenon by which the diffusion actually that the ocean model is seen and is applying to its equations is much larger than the actual diffusion coefficient that we're specifying. And this is a result that is coming from what we call numerical diffusion as a product of the advection scheme. And so Z-coordinate models have this problem. The MOM model, which is the ocean component model, and the Z-coordinate model. And most sort of global scale ocean models and climate models are Z-coordinate models. Yeah.
And so in practice, what sort of shape are those boxes? Is that really what they look like? Or are they a bit more rectangular, or given that the ocean is quite shallow compared to how
yes, that's right. So this aspect ratio, so that your grid box and sort of a regular grid will have large horizontal scales and relatively narrow vertical scales. So for example, if you had a 1 degree ocean model, that kind of means that your horizontal scale, your grid boxes are 1 degree by 1 degree, so fairly large, hundreds of kilometers. And then for a 1 degree model, you might have 40 vertical levels or 50 vertical levels. So that means you're taking a 5,000 meter depth ocean and dividing it into, say, 50 levels. They do tend to make variable depth levels. So you have maybe 5 degree, 10 degree depth bins up top, and maybe 50 degree depth bins down deep.
So what does that mean for your numerical method, which is trying to be stable horizontally and vertically at the same time?
Yeah, it's okay. So the concept of this finite volume modeling, which was discussed yesterday, what we do is we tend to just partition the ocean into these boxes, and it's okay. It doesn't matter what the aspect ratio of that box is, as long as we integrate the fluxes in and the fluxes out to kind of keep a budget of that volume. I don't think there's certain problems with having these really stretched out boxes. Would you agree, Paul?
Yeah, I think that's okay.
Yeah.
How do you deal with like the altitude of the water level change?
Yeah. So that's a big issue. So here they have this nice, there's different things that people do. So there's this, you'll hear this term rigid late approximation, which means that the ocean surface can't deform, okay? And another thing is that you may have a free surface tacked on to your static Z levels, and then you can keep track of that surface height. It's a lot easier in a different representation, which I'll show, which is based on density levels, which we'll get to in a second. Yeah. Okay? All right. Okay. All right, the next one that you have on the shelf to choose from is something that people call terrain following, or a sigma coordinate system. And instead of being based on depth levels, this is based on fractional depth levels that are scaled from 0 to 1. So what I mean by that is the 0.01 sigma level, if you heard that term, corresponds to the first 1% of the depth of the ocean. The 0.5 sigma level is exactly half the depth of the ocean, and the 0.99 sigma level is at the 99% level of the ocean. So what this means is that if you're on the continental shelf and your water depth, say 100 meters, your 0.99 sigma level is 1 meter off the bottom. But out in the deep ocean, where your depth is 5,000 meters, your 0.99 sigma level is 50 meters off the bottom. So this has, the big advantage of this is that it mimics the bathymetry. And it allows you to have high resolution near the seafloor, regardless of how far you are away from the lateral boundary. But there are some disadvantages. These pressure gradients that are so important in the equation of motions, there's some problems with resolving the pressure gradients in this kind of vertical coordinate system. And you still have this numerical mixing problem in this system as well. Yeah?
Sorry, what is diaphysical mixing?
Diaphysical mixing means that you're changing the density of that parcel. So we tend to think of the ocean in the interior as mostly adiabatic. So we move that parcel around without changing its density. And only certain sort of irreversible processes, from a thermodynamic perspective, can diabatically change the density of that parcel. And so one of the problems with ocean models is that actually we have to make that diabatic mixing too strong in order to kind of make them stable. That means they're too viscous in the interior, they're too slow, they're too sluggish, they mix too much. And that too much mixing is coming in part by the fact that we have to prescribe a large diapycnal diffusivity to make them stable, and also because there's this additional numerical diffusivity that's coming from this discretization kind of exercise. Does that make sense? Okay. All right, and then the final coordinate system, which is one of my favorites, is what's called a density or an isopycnal coordinate system. And then sometimes people call these layered models. And essentially, instead of making the vertical coordinate system being defined by depth, we'll define it by density layers. And so you can see that pictured over there. And this really exploits the fact that below the mixed layer, the ocean really likes to follow density surfaces. So it's sort of a natural vertical coordinate system for the ocean interior. So the advantage is that it's relatively simple and it's exactly isopycnal, right? So we don't have this problem now with vertical levels cutting across density surfaces. But there are some significant disadvantages in the global modeling context too. So it means if you define your levels based on density, it means that as you get less stratified, you're losing resolution. And in fact, if you get into unstratified flow, you have no vertical coordinate system at all anymore. And so that means that you can't represent a mixed layer in this kind of vertical coordinate system. So we have to tack on a mixed layer to the top and then match it to our isopycnal interior, and it gets a bit more complicated. Okay, the gold model, which is widely used at ASU, Emma's smiling, is an isopycnal model. All right. Now, you're probably saying, well, gee, some coordinate systems seem to be better in certain regions, and other coordinate systems are better in other regions near the bottom or near the surface. And of course, you're not the first to have thought that. And many people have tried to combine different vertical coordinate systems to sort of best optimize the coordinate system to the region of the flow and the dynamical processes that are active. HICOM, which is US model stands for Hybrid Coordinate Ocean Model. It's really widely used around the world. And it uses Z coordinates in the surface mix layer and then density coordinates in the stratified interior, which is kind of a nice combination. And what's nice about HICOM is actually the vertical coordinate system dynamically reacts to the mixed layer depth. And so it's changing in time and space as the mixed layer changes in space. So it's quite cool, but of course that has some computational cost. Okay? Nothing comes for free. Okay. All right, the third kind of practicality is we have to think about, well, what kind of resolution? Now I've divided my ocean up into a bunch of boxes. How big should those boxes be? Well, before you answer that question, you have to ask yourself, well, what am I trying to resolve? And a little side note here, the ocean, like Steve talked about, the atmosphere, has this wonderful but challenging property of what we call multiple scale variability. And what that means is that in ocean and atmospheric motions, there's not one sort of dominant time scale or one dominant length scale. Instead, we have this broad band of time and length scales on which there's energy in the motions and on which the motions are varying. Further, not only that, we have important coupling between scales. So the large scale processes can couple to small scale processes and vice versa. We call this non-local interactions. And these scale interactions can be really important for both the large scale motions and the small scale motions. And further still, like to make it even more hard, the range of important time and space scales that we're talking about is immense. So we're talking about molecular processes on the scale of millimeters and sort of tenths of seconds, all the way to basin scale processes, which are sort of 10,000 kilometer length scales and sort of 1,000-year time scales. So this makes ocean and atmospheric motions wonderfully fascinating, but also very difficult to model. A few sort of general principles about resolution. There's a lot of different rules of thumb out there. The one that I was taught it takes 5 grid points to accurately define a feature without aliasing. Now it's important to think about what that means. This means if you have a 1/8 of degree global resolution model, you have an average horizontal grid box of 14 kilometers. That does not mean you are resolving 14-kilometer features, right? Really, you need 5 of those cells to resolve a feature correctly. So you're really resolving features on the order of 56 kilometers. Okay, and that's an important thing to remember. Also, you should remember that if your global ocean has variable grid spacing, which it probably does, that means you have variable resolution. So it means that you might not be resolving the same things at the high latitudes where the grid boxes are smaller compared to the equator. And it would be nice if we could just increase the horizontal resolution as much as we wanted, but nothing comes for free, and nothing actually even is cheap. So because of this CFL condition that Steve Sherwood talked about, which basically says you shouldn't have any transport faster than a grid cell in one time step, as you shrink the horizontal grid spacing, you also have to add vertical layers, and you also have to decrease your time step. So a rule of thumb is that every halving of the grid spacing requires roughly 10 times the number of computations. So it's not cheap. Okay. All right. So these global ocean models that come packaged in your climate model often describe their horizontal resolution with respect to their ability to permit or resolve mesoscale eddies. And by mesoscale, we mean the Rossby radius of deformation, the scale at which sort of rotation and acceleration have the same order of magnitude. So there's lots of words out there. People talk about their crappy coarse resolution model or their snazzy eddy resolving model. And there's no specific definition about what these words mean, I don't think. But in general, when someone talks about a coarse resolution ocean model, they're usually talking about models with about 1 degree resolution, and they usually mean there are no eddies in their simulation, no mesoscale eddies. So this is what their temperature field looks like south of Africa in a coarse resolution model. In contrast, if they say, well, my model's eddy permitting, what do they mean? They mean that they're resolving some of the eddies, the larger eddies in the spectrum, but not all of them. And that's usually about 0.5 degrees resolution. people talk about their snazzy eddy resolving models, and this means, I think what this means, people debate. I think what this means, it means that eddies in their model are generating at sort of a realistic rate and with realistic eddy energies. And it usually means that the horizontal resolution is about 0.2 or 0.1 degrees or smaller. I think it's important to point out that eddy resolving does not mean that you're resolving all the eddies. So there is eddy variability at all length scales. So you're still only partially resolving an eddy field. And it also means, I like to point out, that even for the eddies that you're resolving, you're maybe not resolving all their effects. So one of the things that I've actually been working on since I arrived here in a very idealized context is looking at eddy effects as you coarsen in the resolution in your idealized model. And one of the things that we're finding is that to get certain eddy effects right, like how eddies flux momentum to different parts of the flow, is not good enough just to resolve the average eddy size. Actually, that effect has a strong dependence on the eddy shape or the eddy aspect ratio. So in order to get the eddy effect right, if your effect is, say, momentum flux, you need to resolve the smallest dimension of a pancake-shaped eddy, not just its average radius. So it's important to remember that eddy resolving isn't solving the problem. Okay, there's still stuff that's not resolved. Until you start resolving the molecular scale, that will always be true. I Googled last night what's the horizontal resolution of your average CMIP 5 ocean component coupled model, and they list it as between 0.2 to 2 degrees. So that means in your CMIP models, your ocean models are either coarse, so they have no mesoscale eddies, to eddy permitting, so that they're partially resolving your eddy field. We need to we need to parameterize the important effects of eddies in your coarse resolution models. A lot of work has gone into that. But what to do in models that are only partially resolving the eddy field, I think, is an increasingly important problem that needs some careful thought. Yeah?
Is eddy resolving the same thing as having a resolution which is smaller than the deformation radius?
So there's a lot of ambiguity about that definition. That's certainly one definition that people say. So they say that the average eddy size is the deformation radius, which of course is a function of latitude. It's smaller at the poles and larger at the equator. And so that's an acceptable definition. Now, of course, that's the average eddy size. Those are eddies actually that are created by baryclinic instability, have that ratio. There are other eddies that will have different sizes, but that's definitely a generally accepted definition. That's sort of related to this at realistic strength and rate. So what this really means is that eddies due to baryclinic instability that have a size that's like the deformation scale are being generated in your model in a semi-realistic way. Okay. All right, parameterizations. So processes need to be parameterized in a model for two reasons. First of all, we don't want to, for whatever reason, spend the computational resources required to directly resolve them. And this might be because they're too small, or it might be because they're too complex. The second reason we parameterize things that people don't talk about as much is because we don't understand the process well enough to represent it by an equation. And so the processes that in ocean models that we tend to parameterize, Steve gave a list of it in the atmosphere. In coarse resolution models, we're parameterizing mesoscale eddy effects, and I'll talk more about that in a second. We parameterize sub-mesoscale eddy effects, so eddies that are smaller than the deformation radius. Dense overflows, where we form this dense water that spills out into the large ocean basins, that's a big parameterization area. Coastal processes, surface mixed layer processes, friction, subgrid scale mixing, ocean ice interruptions, the list goes on. So there's a lot of very important processes that are represented in these models by parameterization. Generally, in low resolution coarse models, the main problem is mesoscale eddies. And in higher res models, these eddy resolving models, the things that are causing the most problems are sub-mesoscale eddies, so fronts and filaments, internal wave mixing, and details of flow topography interactions. Okay. I thought I'd talk a little bit about parameterizing mesoscale eddy effects because first of all, they're a very important component to your course resolution model that you're most likely to find in your climate model. And second, because it's a nice success story, and so I always like to talk about success stories. So mesoscale eddies, does everyone know what I mean when I say mesoscale eddy? By now? Yeah? Okay. So they have several important effects in our ocean flows, and these include mixing along isopycnals or along density surfaces. They play an important role in re-stratifying or flattening those isopycnals through baroclinic instability. They play a role in what we call non-local fluxes, so taking water in a ring or a meddy and moving it over land. They're a source of small-scale noise and variability, which some people think are very important to the dynamics of ocean circulation. They play an important role in modifying air-sea fluxes. They play a role in kind of moving energy around to different scales in the ocean model, and many, many more. Now, there's sort of two big mesoscale eddy parameterizations in every ocean climate model that you'll work with. And so I thought I would spend just a slide on each of those. You don't need to understand the details on the right-hand side unless you're really interested. So that's the extra activity for the experts in the room. But basically, there are these two critical eddy parameterizations in coarse models are one, an along isopycnal and a long density surface diffusion. This is the ready parameterization. People have heard that term. And the second one is a bolus transport. This is this GM, or Gent in McWilliams parameterization. So starting first with this along isopycnal diffusion, the first mesoscale eddy effect we put on is how the effect of eddies of mixing tracers, so temperature, salinity, anything else you might care about that isn't dynamic, along density surfaces. So eddies play an important role in mixing tracers along these density surfaces. And we can put that effect in without representing the eddies explicitly by prescribing what we call an eddy diffusivity. Here it is, an eddy diffusivity. And in our coarse resolution model, where we don't have eddies, we can prescribe what that eddy diffusivity should be as a function of how steep those isopycnal slopes are. So the ready parameterization, what it's doing is it's putting the effects of mesoscale eddies of stirring properties along our density surfaces, and we can approximate that effect as a function of the large-scale density slope, density surface slope. So that was number one. Number two is this Gent to McWilliams, or GM parameterization. And this, with the along density surface mixing, this represents the mixing effect of eddies by advection, by transport, by bolus transport. And the really important effect of this advective transport of eddies that made the big, huge difference in coarse resolution models is that part of what they transport is something we call isopycnal thickness. What this type of eddy motion is doing is it's acting to flatten tilted density surfaces without mixing density. And so this is an ad hoc way of getting the effects that eddies have in re-stratifying the ocean through baroclinic instability. And we can write that again as an eddy diffusivity as a function of the resolved components of the isopycnal slope. Okay? Now the reason that these two parameterizations is such a success story is because pretty much overnight, by putting in these two effects, so this along isopycnal diffusivity and this bolus transport through these two parameterizations, pretty much overnight we fixed the problem of deep water formation in these global models. So here on the left I show a very old school ocean model, and the contours are showing where they had what we call deep convection. So this is the types of convection where we form dense water and it goes all the way to the bottom. And what you find is that it was widespread everywhere in the high latitudes. They had way too much deep convection, dense water formation. They put in these two effects, and bang, you got deep water formation in these tiny, few localized regions of the world, which is where we observe this phenomenon. And there's this limerick contest going on, and I can't take credit for this, but I found it and I thought it was great. There once was an ocean model called MOM, which occasionally used to bomb. But adiabaction and much less convection turned it into a stable and calm. And so I thought that was nice. I don't know who to attribute that to, but I thought it was very nice. The second really important mesoscale eddy parameterization that you'll find in your ocean climate model has to do with the vertical mixing scheme. And so when the ocean becomes statically unstable, so when the density gradient, the vertical density gradient reverses, we really should have vertical overturning. That's what the physics says. But because most of our ocean models are hydrostatic, it doesn't permit that effect to occur. And so we have to put it in. And how we tend to put it in is by specifying a very large coefficient of vertical diffusion. Now, many models use what's called the K profile parameterization. And again, the details I'm not going to spend much time on. But essentially, this is injecting a very large vertical mixing in the upper ocean due to many processes, but mostly due to wind, and a very much weaker vertical diffusivity in the deep ocean, mostly due to internal wave breaking and tides. Okay? All right. So what are the main sources of errors in our ocean model predictions? I think they come from several places. There is definitely a component of sort of mathematical error that comes from truncation and rounding at every time step. You would think that this is very small, and it is, but if you start to integrate your climate model for tens of thousands of years, it can add up. And so, ocean modelers keep track of these truncation and rounding errors and do some clever things to try to minimize them. A big source of error in our ocean models is actually propagating errors from the surface forcing field. So I blame the atmospheric modelers really for this one. But if you have your surface winds wrong or your surface temperature wrong, that sort of has a propagating effect. So you put too little or too much kinetic energy or in the wrong direction in your upper ocean. The internal waves go off in the wrong direction. So there's many propagating effects that come from errors in the forcing fields. Definitely, we have some errors due to inaccurate parameterizations or approximations that we know aren't quite right, but we don't know how to do them any better yet. We certainly have errors that come from processes that we're missing. And also, one that people don't talk about as much, but from interactions between processes that we're not accounting for. Our parameterizations tend to be process by process based. But I think as we get more and more sophisticated, we're going to start thinking about parameterizing the interactions between processes as well. And then, of course, there's this numerical diffusion issue that's still kicking around. How do we know if our ocean model is right? Well, it's actually very difficult to know. And validation is a big challenge, mostly because there's a lot of unknowns in our understanding about the ocean circulation still, and our observations are very sparse, especially compared to the atmosphere. Things are tough, but they're getting better. The satellite error, we now measure sea surface height, sea surface temperature, and wind sort of globally at the surface. That's helped a lot. And in situ measurements, in situ I mean like in the water measurements, are also improving. We've got lots of different sources. One of the most exciting ones is from this Argo Float program. Who's heard of Argo Floats before? Almost everyone, great. So yeah, so as of yesterday, we had 3,552 floats, all profiling in the upper 2,000 meters, returning via satellite profiles of temperature and salinity. And that's a great way to start validating at least the upper ocean circulation of these ocean models. All right, that's all very nice, but I don't care about the oceans, and really all I want to know is what do I need to get from the ocean in order to get climate change right? If that's how you feel, I would encourage you to reconsider that position. But definitely, if you're just interested in getting the climate state right, there's certain elements that you really need to be getting right in your ocean model. I think they're the following. First of all, you really need to get the heat and the CO2 uptake right. That's a problem. It's very important to your climate projections. You need to have a pretty good representation of the ocean circulation, and in particular, what we call the meridional overturning circulation, which is the vertical circulation of the ocean, the sinking at the poles and the rising. The reason this is so important is because it stores heat and carbon dioxide in the deep ocean, and the details of this overturning circulation tells you how long it's going to get stored before it comes back up to the surface. So that's important for your long-term climate projections as well. It's critically important that you have a good vertical mixing scheme to get both your mixed layer depths right and also your deep water formation in very small and localized regions correct. You also need to make sure you're parameterizing the important effects of mesoscale eddies, because still in most climate models, these are not resolved in the ocean component model. All right, so there are many things still to do, and it's going to be your problems to inherit, so listen up. What are still the problems that exist? Model biases and model drift in ocean models is still a major problem and area of active research. One that's emerging is projections of sea level rise. Someone asked about what do you do about the surface. And actually, this is a bit of a problem in most ocean GCMs right now because we're making this volume conserving assumption. And so as a consequence, right now we must calculate the steric contribution to sea level rise sort of after the fact, which is certainly not optimal. And so that's an area of active research. I read somewhere that the biggest challenge facing physical oceanographers as of today is the realistic representation of mixing. So these diabatic mixing in the ocean. Where does it happen? How much is happening? Why is it happening? This is a big problem just for our understanding of the oceans and also for our ability to model it. This spurious mixing problem is, again, still one that we're trying to solve. It's a bit more complicated because it sort of depends on spatial resolution. So as you vary your resolution and compare your 1 degree model to your 0.1 degree model, this is also changing in ways that we don't fully understand. Dense overflows and how we represent those in models, they're crucially important. We're not quite sure how to represent them very well. A really important one is how do we get the energy out of the mesoscale eddy field. So now we have these nice 0.1 degree, really energetic models, but we don't actually have a good way of getting that energy out of the mesoscale eddy field. We're not representing that in that model correctly. And so as we keep tuning down the resolution, at some point we're going to have to know how to take the energy out of that field. Sub-mesoscale effects and parameterization. Sub-mesoscale effects are probably an important way of getting the energy out of the mesoscale field, but we need to understand how and how to model them. Mixed layer depth and dynamics continues to be an important area. Effects of the internal wave field. We think that the internal wave field is probably very important to the where, when, and how of the mixing problem. But we're still a long way away from resolving internal waves in the ocean in these global models. I think this is a really big one. I think that most of our parameterizations have been written and tuned for coarse resolution models that don't resolve the mesoscale eddies. And I'm not sure if we understand if they're completely appropriate for a partially resolved eddy field and what we should do to them as we keep sort of tuning down the resolution. And so I think resolution-dependent parameterization is a really important one. And another really important one that I know very little about is all the processes related to ice. So dynamic ice sheet models and ice shelf models. Iceberg transport, I was reading, was very important. We have this problem with a cold, fresh bias around Antarctica. And it's been suggested it's because we don't have icebergs that are taking those anomalies out to distant places. And there are many more. Can anyone else think of ones that I've forgotten? Yeah.
Biology.
Yeah, okay, good, yeah. So, I'm a physical oceanographer. Yeah. No, that's right. So biological physical interaction is huge. And, you know, people are very interested in the carbon cycle and modeling the carbon cycle correctly, and that's a huge element of that one. Very good. Any more? No. Good, because we're almost out of time. We're over time. If you want to know more, I'll make sure that Melissa has these resources. I just wanted to flag, MIT has this open courseware program where they put certain lecture notes of their graduate courses online free to anyone. And it's a really wonderful resource. And they have a nice course called Atmospheric and Ocean Modeling. So you can take all the lecture notes and all the assignments, and you can even do the assignments if you want. So that's a good resource. This textbook by Steve Grissies is probably my recommendation if you want to read one book about ocean modeling. And then there's a series, it's funny, I wrote to Steve Grissies about a month ago saying, I'm going to give this lecture on ocean modeling, what can you give me some resources? And he gave me this reading list, and it was all his. But they're all very good, so I do recommend them, and I'll make sure they get on the website. And that's all I have to say. You can just watch another nice movie, courtesy of Andrea Clocker here at the COE. Thanks very much. Any questions? Yeah.
This question might be more suited to atmospheric models. I know some climate models have no ocean. Some
Yeah.
have a simple slab ocean.
Yeah.
I'm wondering what a slab ocean, what advantage it gives over another, particularly with reference to your couple slides back you had what you want.
Oh, yeah.
Represented in the ocean for good climate modeling.
Projections.
So what does a slab, what benefit does a slab over another?
So I think, so a slab model means that the bottom of the atmosphere is being forced essentially by sea surface temperatures, which is important for short-term atmospheric dynamics and phenomenon. What you won't get with a slab model is the longer timescale ocean responses. So in general, if I wanted to predict weather or climate on a very short timescale, I probably only need the sea surface temperature forcing and the atmosphere, because the atmosphere is a much shorter timescale evolving system. But what the ocean does is it has this long thermal memory and this huge heat capacity. And